Okay, well, welcome back, everybody. I've got a small announcement for those of you that are coming for the conference dinner tonight, and there's a list outside if you're not sure whether you are or aren't. What we're going to do, because it's the other end of town. In fact, I'm not even quite sure where it is, in a place called Downing College. So we're going to leave from here a little after 7 o'clock, and we'll walk over. It's like a 20 or 30-minute walk. So join us. Oh, and yeah, if you have clothes that will protect you against rain, it might be worth. Okay, so this afternoon's talk is by David, who will tell us about chiral symmetry breaking from Branes.
So just to remind you, I stopped last time by explaining that we can add massless flavors of left-handed and right-handed quarks to the construction that we were involved in by taking those D4 branes that were stretched in the direction 0, 1, 2, 3, and 4 and adding to them two collections of 8 branes and anti-8 branes that are localized along that X4 circle and stretched in all the other directions of space. And those extra branes gave rise just from ordinary open string stretched between the 4 branes and the 8 branes to left and right-handed fermions, quarks if you wish, that are separated along the extra dimension. And today I'd like to discuss this theory further, and in particular continue thinking about the dependence of the dynamics on the two parameters that I mentioned at the end there. One of which we've already encountered in the problem without quarks, which governed the strength of confinement. In other words, by making it larger, by making, let's say, lambda larger or shrinking the size of the circle, we made the gluons more and more strongly interacting. And now we have this other parameter, lambda over L, which we have to understand better. And this parameter, it's always good to try to think what the answer could be before doing the calculation. And here, it seems likely that this parameter lambda over L, which if you wish just is controlled by changing the distance between the plates, governs the size of the interactions between the left and the right-handed quarks. And interesting things could happen if this interaction becomes strong enough. And so what we would like to discuss today is what actually does happen. And what we will do is follow the same logic we did in the case without these 8 branes and start. So let me say here informally that it governs the strength of interaction between the quarks. Again, just to remind you, the logic of this was that the left and the right-handed quarks interact by exchange of gauge fields and other particles that propagate in this extra dimension. And those particles are governed by a theory that becomes more and more strongly coupled as we go to shorter and shorter distances. So we expect that as the plates come closer, these interactions become stronger. And in order to do a more quantitative analysis here, what we will do is look at the strong coupling limit. So as in the other problem, we will see that we can calculate at strong coupling, and we would like to know what happens at weak coupling. Here, strong coupling means both lambda much larger than R4 in general, and lambda much larger than L, although this one we will see we can actually relax later, interestingly. But for now, let's just start in this region where the analysis without the D8 branes can be done just in supergravity, and we also require this in order for the coupling, the 't Hooft coupling at the scale L to be large. So this is the regime in which I will be working. And in this regime, we know what to do, because we, as we said in the previous two lectures, we can start by replacing these branes by their geometries. So replace the D4 by the geometry, and I will not write again the metric of these D4 branes. I will just sort of draw it qualitatively like this, where this is the radial direction, this is the X4 circle, and of course we have in addition the R3,1 and the S4 that are also warped in some way, but we have already this metric from before, so we will not write it again. Now, what about these objects? What about the D branes? Well, it looks from the picture that they are at some particular points in X4, which is this circle here, and they're stretched in the radial direction. And naively, it looks like they're just stretched all the way. But here, there is no all the way. Space ends at a finite value of the radial coordinate, and therefore, they can't just end there. It doesn't make sense. The space is smooth. So presumably, they, for example, if they were on the opposite sides of the circle, would have to do something like this, right? Go down and then back up. And really, the only thing that they can do is smoothly connect and make this sort of U-shaped surface like this. And of course, if you bring the two D8 branes, the two stacks of D8 branes closer together, it might look more like this. The only thing that is fixed is the distance between the two ends of those things at the boundary, which is, of course, the distance that I denoted by L last time. But what they do in the bulk is just a matter of solving the minimal area equations for a D brane in this curved geometry.
What do you mean exactly by the boundary? I mean, can you go you can't go all the way into the UV, right? Because of the.
Yes. So, well, so technically, what I mean by the boundary is that as U goes to infinity, I insist that the coordinate distance between the D8 branes in the coordinate x4 is L. Now, I can, of course, make it more precise if you insist by following this geometry all the way into the ADS7 cross S4 region at strong coupling.
What happens to the D8 branes in that when you?
Well, so we don't know, but there must be some defects in the 2-0 theory that they correspond to. This is well, we don't know already in type 2A string theory what happens to what is the 11-dimensional interpretation of D8 branes. But this issue will not arise. As I said, technically, what I mean by this fixing this distance L at the boundary is just what I said, that if, as I mentioned last time, there's a very large region in
right.
U where the curvature is small, the dilaton is small, and well, actually, there's more to say about it, but I would like to make a point about this privately later.
Okay.
But I think it's not going to be useful here. Let me. But again, I mean, I just want to make sure that it's understood what I'm actually going to do. There is that metric that I decided not to put on the board again. There's a coordinate x4 in it, which is identified with x4 plus 2 pi r4. That's the definition of r4. And L is just defined as the distance in that coordinate between the two ends of this surface. Right, so this picture, although it looks sort of trivial, is already very interesting because last time I told you that the chiral UNF left cross UNF right symmetry, which from the point of view of the gauge theory just corresponds to unitary transformations acting on the left and the right-handed quarks, is realized here as just the unitary transformations acting on the two kinds of D8 branes. And here we see that they necessarily connect in the bulk, and therefore we cannot make separate UNF rotations on the two kinds of branes. So that, in fact, while if you looked at this picture asymptotically, you would see D8 branes and anti-D8 branes. What you notice when you have access to the whole geometry is that there is just one kind of connected D8 brane, and the UNF symmetry is actually broken. UNF left cross UNF right symmetry is broken to the diagonal one because of this geometric effect. And this is actually, this implies that you have to have breaking of this chiral symmetry just because of confinement, right? Because the fact that the geometry smoothly ends in the bulk had to do with the phenomenon of confinement, as we discussed last time. And this same fact leads for these D8 branes to connect. So what we see here is that confinement implies chiral symmetry breaking. And this is actually something that people argued for in gauge theory many, many years ago, but in gravity, as many other things of this sort, it's much easier to see. Now, these are all pictures. In principle, we have to do a calculation in order to find the shape of these curves, and in particular, things like the minimal value of the coordinate u to which it descends, which, as we will see soon, is actually an important parameter here. And in order to do that, we have to just do the same sort of thing that we've done already a number of times here. We need to minimize the action of the D8 brane. That action is in the approximation we're working in here, where we can use gravity. The dBi action, well, actually there is some overall coefficient that I'm not going to care about, but the action is just equal to the integral over space-time, an integral over x4, an integral over the sphere, the S4, and then e to the minus pi times the square root of the induced metric on this surface. So by this surface, I mean it looks like some curve u of x in the ux plane, or x4, we should say. And it's wrapped around the rest of space, around the R3,1 and the S4. So this is an exercise that I will not do. You can find the action, so let me just write for you the form of the action. Of course, the only parameter I really need to keep is just one of them. I can integrate over space-time and over the four spheres. And the dBi action has some form like this. Integral over x4, u to the 4. Remember, u is a function of x4. And then square root of f of u plus r over u cubed times u prime squared over f of u. So this is the dilaton-induced metric where all these quantities were defined before. So, for example, f of u is something that appears in sort of the Schwarzschild-like factor in the metric. And it looks like that, and r is related to the 't Hooft coupling. So this is a pretty straightforward exercise. You have to solve for the shape u of x given the constraint that I mentioned. And essentially it reduces to solving a first order differential equation. So maybe at least once I will write the kind of equation you really need to solve here. So just standard Euler-Lagrange equation gives something like this here. And this is equal for square root of f of u naught. So in other words, u of x is a solution of a first order differential equation with u naught just being the bottom here. Okay. Now, this is not a very simple equation to solve. It can be done numerically, but let me make a couple of comments about it. So one place where it simplifies is when this L is equal to pi times R4. So that basically means that the two endpoints are exactly halfway across the circle from each other. And then it's clear what this d8 brane does. It just goes down all the way to the tip and then back up. So then the solution is easy. And the other case in which this equation simplifies and can be solved in closed form is when L is much, much smaller than R4, or even for simplicity, let's say you send this R4 to infinity. Then, again, just on the level of solving these equations, so then, of course, f of u becomes 1 because this ukk goes to 0. And you can just solve the equation. So you find, in this case, that x4 of u is equal, just to show you that we can actually write explicit formulae here, you get something like this. So plus and minus just has to do with the two branches of the solution. The plus is, say, this half, and the minus the other half. And then there is some Bernoulli function. So 9 over 16 and a half. And so this is the excuse me, Euler, not Bernoulli, beta function. And then this, from this you have to subtract an incomplete beta function. This is an incomplete beta function. Okay, so you can solve this equation in this limit, and actually when you send u to infinity, you better get L, or L over 2, from this limit. And so just by evaluating this as L goes to infinity, you find something like u naught goes like lambda over L squared with a coefficient that has to do with these Bernoulli functions, excuse me, Euler beta functions that I will not write. So this is the analog of the fact that this ukk we found last time behaves like lambda over R4 squared. So this is what you get from solving these equations. But now let's think about the meaning of all of this. This actually has some rather interesting physical interpretation, which I would like to explain. So first of all, let's talk about this limit, which turns out to be particularly instructive. R4 going to infinity. So if you think about it back in the original picture, it looks like there's no hope of getting anything non-trivial, right? Because when R4 is infinite, the theory that lives on these D4 branes is 4 plus 1 dimensional. And there is no confinement. The confinement scale goes to 0. And so how could we get anything non-trivial? In fact, what you would expect to have in this limit is precisely the kind of picture we've drawn there, that the D8 branes just look in the geometry of the D4 branes like two infinite planes. Now, in fact, what we got, if you think about the geometry corresponding to the D8 branes when u of x has the form described by this Bernoulli, this Euler beta function, is a shape like this. Basically, what we discovered is that the minimum energy configuration for these D8 and anti-D8 branes is one in which they're connected by this tube, and the size of the tube is u naught. So this is the minimum energy configuration, And in particular, it's for the reasons that I mentioned before, it is one where the chiral symmetry is broken. The UNF left cross UNF right symmetry of the original picture we started with is broken because the two sheets here are connected. And not only that, it's broken in a bad way, in the sense that this tube becomes wider and wider as the distance between the plates decreases. So as you bring these plates closer together, the tube becomes wider and wider. So you can ask, well, how did that happen? What is going on here? It seems like it's inconsistent with our intuition that all these quarks here are doing is just exchanging 5-dimensional gluons. And in fact, it's true that that's what they're doing, but the answer we got actually makes perfect sense, because those gluons in the regime that we are discussing right now, which is this regime, do become strongly coupled even though they're 5-dimensional. So the fact that we have just relaxed this condition and sent R4 to infinity means that the gluons are 5-dimensional and weakly coupled at very long distances. But what these quarks are doing is probing their dynamics at short distances, at distances of order this L. And at that scale, which is very short, these gluons are strongly coupled. So in other words, what we have here is the left and right-handed quarks interacting by exchange of some pretty strongly coupled 5-dimensional fields. And this interaction is apparently strong enough to break the chiral symmetry, to generate a non-trivial condensate for the quark bilinear.
Is this stable?
Yeah. Well, so that's, if I understand your question correctly, you're asking whether small fluctuations about this solution have tachyons. Yes. So no, they don't have it. It is stable. This is the absolute minimum of this action with the boundary conditions I specified.
And it would start developing instability if the plates are close together, the D8, D8 bar?
Wait. I probably missed you. You're asking about now something different, which is whether these D8 branes over here someplace want to collide for reasons that have nothing to do with what I'm talking about. Is that what you're asking? Just because gravitational exchange and things like that. So it's believed that the answer to this is no, but I don't have time to go into the arguments. I'm happy to talk to you about it later. But I'm not addressing the question. So the question you are asking is not really that well addressed by studying this action. I mean, in principle, you should ask whether, well, if you're doing this in the full flat space, there would be the issue of whether exchange of gravitons between them somehow leads to an instability where the whole thing starts collapsing on itself. And we're not in a asymptotically flat space here. We sort of threw away the asymptotically flat space. And it's believed that that's good enough. But I don't have time to discuss.
You're saying that if we would quantize modes in this background, the tachyon would increase, will get closer to zero, or maybe even...
No, well, even in flat space, there is no tachyon here, right? We're discussing branes and antibranes some enormous distance apart in string units. The issue is just, in that regime in flat space, some kind of gravitational attraction. So in flat space, they would sort of slowly start moving towards each other. It would take them a while. But again, we took some kind of decoupling limit here, and we got rid of that. I mean, this is not an easy issue, and I don't want to go into it here.
Do you recover any supersymmetry in this limit? Now you can forget about your anti-periodic boundary conditions for the, or is it still broken completely by the?
Well, it's broken completely by the A bar branes, and the easiest way to see that is that the low energy theory is non-supersymmetric, right? So the low energy theory, for example, has fermions but not bosons.
But the bulk theory becomes.
The D4 brane theory, of course, or to say it in a different way, the background before you put in these branes is now supersymmetric. Yeah.
Bulk in that sense.
But the branes break all supersymmetry, of course, still. Okay, so in fact, what I was getting to is that this is actually a realization of an almost 50-year-old idea due to Nambu and Yona Lasinio, who basically proposed around 1960 or so, I think, that you can have a mass generated for fermions just by having strong four-Fermi interactions. Then I think there was no confinement or anything, but quite separately from any questions about confinement, they wrote an interaction Lagrangian that in my notation would be something like Q dagger left dot Q right times Q dagger right dot Q left, and showed that if the coefficient in front of this is sufficiently large, the quark bilinear develops an expectation value, and the quarks themselves therefore develop a mass. But that model was never under control in 4 dimensions. Of course, in 2 dimensions, it's the Gross-Neveu model, which is asymptotically free and has the same phenomena in a controlled setting. But in 4 dimensions, this model was not under control because it's not renormalizable, and most of the interesting phenomena happen at the cutoff scale. But here, we basically get a realization of this idea in a context that is controlled. This is what these branes do. They have, there is no confinement here. The gauge bosons are 5-dimensional, but those 5-dimensional gauge bosons produce the kind of strong force that is needed to generate a mass for the fermions. And in fact, it's not even a small mass. It's a mass that is arbitrarily large in terms of the parameters of the theory. So if you plot energies the way I did in my first lecture in this regime here, so the smallest energy that is relevant in this system is 1 over lambda. The next one is 1 over L. And this mass, the natural mass scale that arose from this exercise we just did, that I will explain in a moment, which has to do with the fermion mass, is actually the largest of the 3 by a large factor in the regime we're interested in. So this is a large mass generated here by these interactions, and it becomes larger and larger as the plates come together. Now, why am I calling this the fermion mass, the mass of the quarks? The reason I'm calling it a fermion mass is that what were these quarks, after all? To start with, these quarks were little strings that stretch between the 8 branes and the 4 branes, right? Now, here we don't have the 4 branes anymore. We replace the 4 branes by their geometry. So instead of the 4 branes, there's a singularity at u equal to 0. But you can still convince yourself that there is a good sense of thinking about a fundamental string stretched between sort of the bottom of this tube and u equal to 0. And such a string is precisely one of those fermions. I mean, if you want to be a little bit more precise, what you would talk about is a fundamental string that starts on this tube, has another end somewhere on this tube, some large distance away in one of the directions in R3. And what such a string would want to do is just go down, stay there, and then go back up. And the energy of such an object would be proportional to, or equal actually, I think, to u naught, to this mass here. And this is the mass of the fermion. So the model does not confine. There exist asymptotic states in the spectrum here that are the fermions. Their masses are this big. The fact that they exist in the spectrum is just a statement that if, as you separate the two ends of this fundamental string, the energy does not grow with the separation. It just goes to twice U naught. But because of the sort of effect that Nambu and Ioannou-Lesinio envisioned all those years ago, the fermions get a mess. So that's what happens in this limit that I described here in detail.
David, you can see a first order transition at some critical L.
Yeah, actually, let me get to that. There's an interesting, let me address this a little bit later. What I'm planning to do is first talk about the strong coupling region, and I have a few things more to say about it, and then I'll get back to this point. Yeah.
So the static quarks are confined, static sources are confined.
No, that's the point. They're not confined, right? Because when I discussed this model before, I talked about a situation in which this R4, well, if I wanted to be in a situation where I wanted to be able to calculate, I took the radius of the circle to be much smaller than the natural scale of these D4 branes. And there I explained, as you say, that static quarks are confined because of the fact that the geometry ends at a UKK like this. But now I'm here in this story here. I started out somewhere on this board by sending R4 to infinity. And in this limit, that cigar that I was talking about before goes down and hits U equals 0. And that same calculation I would do like last time to look at static quarks would tell me that they're not confined, right? Because the confinement of the quarks, of those static quarks, has to do with the finiteness of the warp factor at the bottom of the space. And the square root of GTT times GXX. And here, now, you know, the reason I didn't discuss it last time is that I have nothing useful to say, not just in this limit, but even before it, in the limit where R4 is large but still finite, much larger than lambda. That's the region in which I said the whole thing is described by Yang-Mills theory and I don't know how to solve it. The reason I'm talking about it here is that once you add the quarks, it looks like it doesn't matter whether there is confinement or there isn't confinement. In the limit I'm talking about, there isn't confinement, but the quarks just develop you know, a large mass in some other way. And the other way is this Nambu-Ioannou-Lesinio kind of way.
And is it clear that such quark carry baryonic charge?
Well, by definition, right? Baryon number is just the
Baryon number is
U1.
related to S4 wrapping.
Oh, that. Well, of course. Right. I think the answer is yes, but yeah.
Can you see what plays the role here of the Gaussian boson?
Yes, so, the next step in this process will, of course, should be complicating. So here I got rid of everything other than the function u of x4 that I was interested in. The next step is to look at small fluctuations about this background. So I have to say that, for example, my u is a function of x4 and x mu, and introduce the other fields like the shape and the size of the S4, etc., and look at the spectrum of small fluctuations. And when you do that, you find, on completely general grounds, indeed, as you would expect, a massless mode that corresponds to a fluctuation of the surface. Of course, you can phrase it, you can describe it in different ways because of gauge invariance. So one way you can describe it is just as a mode of A4. So on the D8 branes, there is a gauge field, and that gauge field has a 4 component. And so you can look at small fluctuations of A4, and one of them is massless and corresponds to the pion. And of course, it's not just one scalar, it's an NF by NF matrix. So this is the Goldstone mode of the breaking of UNF left times UNF right to UNF diagonal. And actually, while I'm at it, maybe, well, that's one of my comments. Let me say the rest of it. Well, okay, so let me make a few comments about this. And one of them will be a continuation of this story. Let me continue my answer to David and comment a little bit on the spectrum of mesons. So what I mean by mesons is what I just said. You expand the dBi action around the solution and look at, just diagonalize the small fluctuation operators. So you get NF squared pions that are the Goldstone bosons for this breaking. And then you get massive fields, massive particle states, massive mesons, you might call them. Now, the mass scale, so I'm not going to do, I just don't have time to do this exercise here. The mass scale for these mesons is, as you might guess from what we've done last time, around 1 over L. So if you go back to this picture here, the mesons, which are the small fluctuations of sort of light open strings around this background, have these kinds of masses. Now, at first sight, it looks very strange because the fermions out of which these mesons are made are very heavy, right? So lambda over L squared in the region we're working is much, much larger than 1 over L because lambda is much larger than L. And it looks like it's strange to have two heavy particles create a very light bound state. So these mesons you should think of as Q bar pairs, and they're much lighter than the constituents. So the binding energy is more or less 100%. But if you think about it from the point of view of this construction, the string theory point of view, it's not at all surprising because, as I mentioned, the fermions are these kinds of strings. They are strings that go down from the bottom of this tube to u equal to 0, whereas these QQ bar pairs, since they're allowed to come back, can be just short strings. There's no reason for them to make all this journey down the tube. And so they can be much lighter. And so what you really have in this model, you do not have confinement, but you have something, morally speaking, similar to it. You have meson kind of states at energies of this sort, and then at a much, much higher energy, you will be able to liberate the actual quarks out of which these objects are made. So, I mean, I'm of course not trying to pretend that it has anything to do with QCD right now for the reason they mentioned in the first 2 lectures, but this is the kind of physics that this model describes, and you know, so people tried to look at these mesons, at the states with energies of order 1 over L, vector mesons, scalar mesons, etc., and compare them to the meson spectrum of QCD, and it actually doesn't look as bad as you might imagine it will. Again, the sort of things that we were discussing the other day, for some things 15-20% agreement. You can even work the numbers so it's better in some cases. But this is the kind of physics you can get out of this model as far as the mesons go.
David, can I ask you a question?
Yes.
I'm a bit confused. So you have kind of symmetry breaking, right? So you have a quark condensate, right?
Yes.
So so the pion mass square should be the quark mass times the quark.
No, oh, sorry, excuse me. I probably misunderstood. The mass of the quarks is 0 here. In the original model, yeah, okay, I understand why you got confused. So there are two notions of quark mass,
Right, so we are
right?
talking
One
about
is
the constituent
what
of
is
the
usually
carbon.
called the constituent quark
Okay,
mass,
yes, so that's my question.
is that 300 MeV, out of which everything is made. Although the U and D quarks are very, very light, right? So so U naught. Okay, so I probably should say more about this for people who are not familiar with it. So U naught is what you would call the constituent quark mass. In other words, this is the mass that these quarks have after you took into account quantum effects, chiral symmetry breaking, and all of that. So this is the analog of the statement that the U and D quarks as constituents of protons have mass of order 300 MeV. If you put 3 of them together, you get 900. What is usually called the current algebra mass of these things is equal to 0, or the Lagrangian mass, I don't know how you like to call it. And that is simply because there is, the way to think about it is that in order to give these things a mass, you basically would have to separate the D4 branes and the D8 branes, and you can't. They don't have...
Always 0 in this model.
Yeah, in this, yes, well, yes and no. In what I've said here, it is 0. There is a way to introduce a mass, but it's not known how to do this in detail. So how would you introduce a mass if I forced you to? Well, what you would say is that you want to add to the so this is an example of a bulk boundary correspondence. So you want to add to the Lagrangian of the boundary theory a term that goes like Q dagger Q. So you have to find the operator in the bulk that couples to the operator Q dagger Q. I mean, this kind of operator.
Right, but usually we are inspired to look for this kind of relation from the flat space, and it's suggestive that it's impossible in this
No, I don't have any inspiration. So again, you want to add to the Lagrangian of the boundary theory this thing. So if I give you the operator in the bulk that couples to this thing, then there is a general technique how to do it, right? You just add the non-normalizable mode of that operator and you're done. Now, one thing that you can take from the flat space picture is that the lowest lying mode of the string that goes from here to here definitely couples to Q dagger left, Q right. Right?
So in other words, you're saying that in the flat space limit, the massless, the quarks are always massless. But there is a way
Well, I
to
would
give
say
the mass that strong coupling.
no. I would say here also, again, we're going in directions that I did not intend to go. So let me just say one word about it and we can discuss it later. Also in the massless limit, you can turn on, you can do what I'm about to say, but it just involves going away from the free worldsheet theory that you started with. You know, in flat space too, right, you can add deformations that take you away from free field theory and study them. It could be harder, but you can do that. And what you need to do is give an expectation value to such a string. So the lowest mode of this string is usually called the tachyon, because it's a string going between D branes and anti-D branes. And you can try to do it in the geometry there. But you know, it's an open problem how to deal with it, how to solve it, because what we're doing here is just solving supergravity, and you know, with Branes, and the tachyon is a non-trivial bulk perturbation that would need to be solved from. So one other interesting fact that we learn from this story is that we can have chiral symmetry breaking without confinement, this is what we just discussed, but not the other way around. Right, which is also something we've just discussed. So if we have confinement, in other words, if this cigar has a tip at some finite u, then the D branes have no other option but to connect. That means that if you have confinement, you have chiral symmetry breaking. But as we just saw, if you don't have confinement, if the tip of the cigar goes away, you can still have chiral symmetry breaking in this kind of non-Bouillon-Lusinio mode. And maybe a more precise version of this is that just by construction here, the mass of the fermion is by definition larger or equal than the mass scale associated with confinement. So it's a more precise version of this story. There's also thermodynamics that you can study. And here, again, you can just proceed in the way we've done before. So without the D branes, without the quarks, we saw that for temperatures lower than a certain temperature, you're in the confined phase. So in the confined phase, there's nothing to talk about because of the previous point. In the confined phase, at temperatures smaller than the deconfinement temperature, we have chiral symmetry breaking here. And in the deconfined phase, we have to work. So remember that the deconfined phase corresponded to this situation where U and X4 just formed a tube that does not close. So this was how the radius of X4 looked, and in X0 we had this black hole sort of geometry. So here you have to do the kind of exercise I was doing before. So the branes need not connect anymore, the D8 and D8 bar branes. So you have to figure out whether they want to do this or this, whether they want to be connected or disconnected. And there is an exercise that needs to be done, and you find that there is a chiral symmetry restoration transition. So again, I will not have time to go through the details of this analysis, but it's of the sort I've written here. So what you find is that chiral symmetry is broken for temperatures lower than some, let's call it T chi, and restored for temperatures larger than T chi. And the interesting question is whether this chiral symmetry restoration temperature is the same or different than the deconfinement temperature. And so what you find when you do this exercise is that for L, which is of order R4, the chiral symmetry restoration temperature is equal to the deconfinement temperature. And for the kind of regime that we were working with here, if R4 is much, much larger than L, then the chiral temperature is much larger than the deconfinement temperature. Well, just, yeah. So in other words, there is sometimes a hierarchy between the different temperatures. You can reach the deconfinement temperature and still be in the chiral symmetry broken phase, and then chiral symmetry breaks later.
How do you evaluate these temperatures?
Well, I basically showed you how to do this. By which I mean the following. So I told you the background that the D4 branes have around them. So as I said, in the confined phase, there's nothing to talk about. in the deconfined phase, you take that background that I wrote down for the D4 branes. Now you take the DBI action that I also wrote down, and you ask this kind of question, whether the lower free energy configuration or the lower DBI action is for a configuration where they make a U like that, in other words, where chiral symmetry is broken, or whether it's when they disconnect. And what you find is that the answer to this question changes as you change the temperature, in general at a different point than the deconfinement point. So I think the main thing that this model stresses is that in general these two phenomena of confinement and chiral symmetry breaking are just two different, separate physical phenomena, something that was sort of clear already from, well, from the Nambu-Yono-Lasinio model, and say in 2 dimensions, say in situations which are under control, it's clear from a combination of the 't Hooft model and the Gros-Neveu model, right? Because the Gros-Neveu model is an example of a model that breaks chiral symmetry.
That's the case in QCD.
Sorry?
But we don't know whether that's
Oh, no,
the
no.
case.
No, again, you know, as I said, I said before, and you know very well, that these gravitational models live by creating hierarchies where none exist in QCD. In QCD, you do not have a spectrum of Kaluza-Klein modes followed by Regge trajectories. And you also don't have a hierarchy between the deconfinement temperature and the chiral symmetry breaking temperature. But I guess what's nice in these models, both, you know, not just in respect to the chiral symmetry breaking issue, but just in general, is that when you separate the Kaluza-Klein scale from the Regge trajectory scale, for example, you get models that are solvable, that you can analyze. And then you might hope to come back to in the direction that you're interested in going. I mean, I still owe you an answer to that question about what happens when you get there, when you go in the direction of weak coupling. But I mean, I guess what I was trying to say is that in field theory, in situations that are under control, people knew already in the 70s that you can construct models that break chiral symmetry and do not confine, and you can form models which confine. Hooft model that can be analyzed. In 4 dimensions, I would say there were no sort of tractable models, quite separately from the question whether they have to do with QCD or not, that can be analyzed, in which this question can be asked. And these examples are examples of models where we can ask and answer this question. And again, you know, in this model too, this is something I probably should stress. There is a so this L, right, so you have a cylinder for x4 of circumference 2 pi r4. So L is the distance between the two branes, so it's by definition smaller or equal than pi r4. And there is a finite range of, so in the regime in which I'm working, where I can trust supergravity, there is a finite regime of L's between pi r4 and some r critical, in which these two temperatures are exactly equal. And it's only when L goes below that that this difference appears. Okay, and the nice thing here is that you know, if you want, you can be in this regime where they're the same and you can solve, or you can go to a regime like the one I was discussing here and you can still solve. And it's just the more important qualitative point is that they are different physical phenomena in 4 dimensions. And that's something that, for example, to me was not clear before, whether, you know, if you have confinement with chiral symmetry, is it automatic that, you know, do you need confinement to break the chiral symmetry? Is that the source of the mass or not? And here we see examples where it's not. Okay, so let me now come to the question that David was asking before, which is what happens when we now leave the strong coupling regime and move into the opposite regime where everything is weakly coupled. So there, just like in the problem without quarks, we very quickly lose control and have to resort to generalities. So weak coupling in general means that lambda is much, much smaller than R4, and it's also much, much smaller than L. Well, if you start going in this direction, it's clear. So what would you say just by looking at the answer? So the mass of the fermions, as, for example, L increases, starts going down. And at some point, when it hits these two scales, the 1 over lambda and 1 over L scale, you lose control. So if you just naively extrapolated, you would say that the mass of the dynamically generated mass of the fermions coming from this model will decrease as you go towards weak coupling. And the question is, what will happen next? So there are two different limits in this regime that you might want to talk about. The first is a limit in which R4 and L are comparable, and both are much, much larger than lambda. Then I would say that we're just dealing with QCD with massless quarks. You can argue convincingly that the low energy theory of this model in this regime is just QCD with massless quarks, and it does whatever that theory does. Whatever you believe it does, that's what happens here. And what we believe, of course, it does is confinement plus chiral symmetry breaking at some scale, lambda QCD, which, as I mentioned before, is of order 1 over R4 e to the minus 1 over the 't Hooft coupling. So here, nothing much to report. The interesting question is, if you are in this sort of regime, so suppose you even took R4 to infinity, so you don't, confinement is not an issue, or yeah, so even take this R4 to infinity, and now ask, as we said, even if R4 is infinite, when L is small enough, we can just trust supergravity and the dBi action for these D8 branes. So the question is, as we now increase L so that this tube becomes narrower and narrower, what happens when we get to this kind of regime where L is very large and the coupling is small? And in particular, what you would like to know is whether the mass of the quarks as a function of lambda over L does, well, so what you know from the strong coupling analysis, it does something like this. In the middle here, there's some region where you don't know what's going on. And here it could do one of two things. It could either go smoothly to 0, or it could be just 0. So phase transition or no phase transition at finite value of L. Now, well, the short answer is that it's not known what happens. The most naive thing that you would say is that you expect a phase transition, because the model that you should analyze in order to answer this question is 4 plus 1 dimensional SUNC gauge theory with two defects at which you have left and right-handed fermions on the infinite line. And intuitively, we would say that the interactions are just too weak. So for example, if you do a one gluon, if you allow these quarks to exchange a single gluon, you get a quartic interaction between them that is weaker than that in QED. And we know that QED does not, four-dimensional QED. And we know that four-dimensional QED does not break chiral symmetry. So the most naive thing to expect is a phase transition, some story like this, where at some L of order lambda, it just drops like a stone and just stays there. But that would be interesting. That means that this D-brane model has a phase transition, unlike, for example, n equal 4 Yang-Mills, which is not expected to have a phase transition in a similar context. And if it does have such a phase transition, we probably should be able to say something about it. My feeling is that it's not exactly clear at the moment. It could be that once you include higher gluon exchanges between those quarks, something less trivial happens, that there is actually a vacuum where well, the true vacuum has chiral symmetry broken so that this curve is smooth. But that would, if that is true, that would be a new phenomenon in field theory, of course. It would be some statement that 5-dimensional Yang-Mills theory coupled to 4-dimensional defects of this sort has this amazing new phenomenon that you should in principle be able to treat using field theory techniques because it's all weak coupling.
But when L is very, very large, right?
Yes.
You should be able to make it arbitrarily weakly coupled.
Yes.
That solves the whole situation.
Yes.
So you
Well,
should be able to analyze it. If there is an exponential tail, it should be some
yes.
semi-classical effect that still present but exponentially smaller.
Yeah. So, well, of course, even if there is a mass generated, it would be, what you're saying is that this mass, if one is generated, would be exponentially small in L. It would go like e to the minus L over lambda or something like that. I completely agree with that. And you should also be able to see it using some kind of field theory techniques.
Well, as you certainly have as small a coupling as you like in that.
Exactly. And not only that, I would also add to that that it's even a vector model, like the Gross-Neveu model, for example, because in some sense, the 5-dimensional gauge fields are not really dynamical, right? Because they just provide the interaction between the 4-dimensional quarks. And anyway, I mean, it's an open problem. I mean, I think I would not give it more than a 10% probability to give this kind of answer, that there is actually a non-zero condensate. But the alternative is also interesting again. The alternative is a system of D branes in string theory, which you can analyze in the gravity regime, and it does something. And then as you smoothly change the parameters, there is a phase transition at the finite value of the coupling. In this case, lambda over L. So it's an interesting possibility. I don't know, what will eventually be the resolution, but I think these are the options at the moment. Okay, so this concludes the part of these lectures that deal with QCD on Branes. So if there are any other comments or questions about this, this is a good time. And so for the remaining part of my lectures, what I want to do, as I said in the beginning, is talk about a slightly different subject, which is how to realize supersymmetric QCD and some metastable vacuum that it now is known to have in string theory. And on the way, we will also discuss how Zyberg duality, which I guess you must have been hearing about from Brian Wecht, is realized in this theory as well.
Before you get your
Yes, I'm sorry.
question, it's just that over there you were explaining that you have a model in which it looked like a confinement theory up to a certain energy and then suddenly
Right, yes.
discover it's not really.
Right.
How do we know that situation does not apply in the real world?
Well, I think the reason we know is that we have very good evidence that we know the Lagrangian, right? We know that QCD is a good.
That was my question. How do we know that QCD is right when compared, when compared to possible other models which have the phenomenon that you were telling us about?
Well,
I realize the Nobel Prize is awarded.
well, okay. Setting aside Nobel Prizes, I think my understanding is that the most important point is that QCD is most well tested in the regime where it slowly approaches its asymptotically free behavior. And it is that part of the story that would be, so, if you just knew that I have a pion and I have the rho meson, and if you just saw these particles, and you have never done the slack deep inelastic scattering experiments and you didn't measure those logs very exquisitely, you might have asked those questions, like in 1970. But it seems to me that the case becomes much harder to make once you know that at energies of 2 GeV or something, things already start running very, very nicely towards a free fixed point described by that Lagrangian. Now, it could be, I mean, of course, we all believe that, you know, it's not like QCD, the SU3 Lagrangian is true up to 10 to the 19 GeV, you know. It gets replaced by something, but it's in a regime that we have no interest in for this, the present discussion. That's right. Well, but okay, but I think Paul is saying that forget about UV completion, just, you know, how do you know that if you smash pions very hard together at an energy of 100 TeV, right, you will not all of a sudden see a quark and an anti-quark propagating to infinity. And it seems to me that, well, you say it could be that when you get to really high energies, somehow. Yeah, no, I'm of course, I understand that we're, yeah.
Raising the possibility. I mean, you have a model which exhibits that phenomenon. So
Yeah, no, I guess at a completely different energy scale.
yeah.
So I guess we don't know, right, that at 1,000 TeV, like if you smash pions together with Mandelstam invariance of 100 TeV, it could in principle be that you will be able to liberate the quarks just because it's described at that point already by some other dynamics. I mean, well, I don't know, what do you think?
I don't see
A viable scenario.
I mean, this doesn't
Oh,
give that picture.
I think the question was more.
Mesons, right?
The question was. The question was, I think, not whether this model described the world, but how do you know that quarks cannot be. There are no states in the spectrum that look like free quarks with some enormous
It's a
energies.
little difficult because you'd have to be approaching a UV fixed point, right? Because that's what we measure over, 3 orders of magnitude, and then you'd have to have some unstable direction, which would have to have an incredibly small coefficient somehow. Right? Like some QQ bar squared or down or something.
Yes. But it's not impossible, right? It could be. I mean, yeah. I mean, yeah. I think that's actually a good point. So I think one way of thinking. I think what David is saying is that a good way of thinking about it is that you can do such things by adding to the QCD Lagrangian terms like QQ bar squared, let's say, right?
Well, we know they're there. You add to the QCD Lagrangian terms like Einstein action.
Right.
At some point, we know that QCD isn't right. It's
Right.
There are other things.
Okay, but
The only question
it
is
could.
when they
I
come
think
in.
the question is, could the other things be of this sort that indeed take you away from the free fixed point in a direction which allows?
Right, but they would have nothing to do with the mesons that are at a totally different scale. They're much larger. They might have to do with mesonic states above that scale.
Mhm. So you well the question. So you think that we can
Because
argue
gravity,
convincingly?
We have to worry about gravity in calculating meson mass.
No, I mean it could be some intermediate scale.
We think we have to worry about them when they get to be scale mesons.
Mhm.
Light mass.
Well, we could in principle see non-integer charged states at some enormous energies, right? This would not be in contradiction with the standard model if those energies are. Well, the truth is, I don't know. I mean, that's a good question. I don't know. I think it's some sort of model building issue. And at scales that are so far above the ones we're currently studying. But it's indeed an interesting question. Okay, so in the 5 minutes that remain, let me just say a couple of words about how I plan to get n=1 supersymmetric QCD from string theory, and then study supersymmetry breaking in it. So we're going to again use D4-brane dynamics. In other words, this n=1 supersymmetric QCD will live on D4 branes, but we will need a couple of new elements. So one new element that we will need is something called Navier-Schwarz 5 brane. And so let me just mention briefly a few properties of these things. So they are magnetic duals of fundamental strings. In other words, just like fundamental strings carry charge under the B mu field of string theory, these carry the magnetic charge under that. They have a large tension. Goes like 1/G string squared times L string to the 6. They're 5 branes, so their energy per unit volume has units of mass to the 6. And because it's so large, they curve space around them. Already in leading order in G string. And I guess the other thing that I should point out about them is that they preserve 16 supercharges, which is 1/2 of the 32 supercharges of type 2 string theory. Type 2A in the case we will be working in. And the second element, well, and I guess the other fact that I will use about them is that D4 branes can end on them. So this can be explained in much more detail, but I'm beginning to run low on time, so let me just have you trust me on this. So in order to realize n=1 supersymmetric Yang-Mills on D4 branes, what we can do, and I will just finish with this picture and a few words about it, is the following, is put a brane that, just in order to not talk about the directions in which it's stretched too much, I will call an NS brane, and it's stretched in these directions 0 up to 5. And then some distance away in the x6 direction, you can put another brane, which I will call the NS prime brane, which is stretched in the direction 0, 1, 2, 3, 8, and 9. And along the line separating them in x6, I will stick NC D4 branes, which are stretched in the direction 0, 1, 2, 3, and 6. So I'm using here the fact that I can actually do this without running into contradictions. So first of all, you can check, and again, I would be happy to do it if I had more time. You can check that this configuration preserves 4 supercharges. So each of these objects preserves half of the supersymmetry. So we have 32, and then it gets half by each additional object that you put in. and you can find the formula for which half each of them preserves in, say, Polchinski. So you can check that indeed they are compatible with each other in this way. And moreover, it's pretty easy to see that the spectrum of states on these D4 branes is just that of U and C n equal to 1 super Yang-Mills theory with no matter. So if you want to understand where that comes from, in qualitatively speaking, you can think about it in the following way. So, so what really lives on D4 branes, as I mentioned in the beginning of these lectures, is the gauge field and then some scalar fields. And the scalar fields just parameterize translations of these D4 branes in some transverse directions. And all of these scalar fields are fixed either by the fact that they end on this NS brane or the fact that they end on the other NS branes. So the scalars are all massive. And so the only massless fields are the gauge field and its superpartner, which is the gaugeinum. And of course, because of the usual fact that we have UNC on NC of these D4 branes, it's UNC, n equal to 1 super Yang-Mills theory that we're dealing with here. So there's plenty more that I want to say about this, but I think time is up, so let me stop here and continue tomorrow morning. I'm sorry, I can't. In this kind of model?
Well, in any of these kind of stuff.
Yeah, I mean, there are models with orientifolds and all sorts of things like that, which have chiral meta representation. So the kind of thing that you can pretty easily do is have some SUN gauge theory with, say, anti-symmetric tensor and some anti-fundamentals that cancel the anomaly. That there are constructions of this sort that do this.
Any other questions? Thank you, David, again.